Let's take a look now at the idea of finding a limit based on the table. We've already done something very similar to this. Now, suppose you're asked to graph the function f of x equals x squared minus 4 over x minus 2. Now, for values of x not equal to 2, you could use some standard curve sketching techniques. Put in values of x, set up an xy axis, put out a dot there, connect the dots, that sort of a thing. But what happens when x actually equals 2? Well, if I do this, if I find f of 2, I get 2 squared minus 4 over 2 minus 2. That's 0 over 0. What on earth is that? Well, that's actually called an indeterminate form, which we will get into in a great deal of depth a little bit down the road. But for right now, we're going to say that this thing is undefined. This doesn't mean anything. 0 over 0 is not 1. Please don't think it's 1. This is an indeterminate form. We don't know what the heck this thing is. So I want to consider values of x as x approaches 2 from both the right and the left. And this is going to give us a good idea of what the function is doing near x equals 2. To do that, let's go ahead, like I did previously, or in a video sometime back, let's bring up Maple, put this into Maple, and start picking values very, very, very close to 2, like these values here, and see just what's going on. Okay, so the function f of x is equal to, let me make a real small adjustment here. That might make it a little bit easier to see. There you go. F of x is equal to, see, the numerator was x squared minus 4 divided by, the denominator was x minus 2. And yes, I want to make this a function. So there, now I have this thing set up in function notation so I can quickly and easily evaluate it. So what is f of 1.5? Well, what I'm going to do is I'm going to start putting in these values to fill in that chart. Well, f of 1.5 is 3.5. Well, what is f of 1.9? See, I'm starting to get closer and closer to 2 now. That's 3.9. Okay, well, maybe it's getting close to 4. So what is f of 1.999? That's 3.999. Well, that really looks like it's getting closer and closer to 4. What is f of 2? Oops, 2, not 20. This is the way Maple's saying, you goofball, this doesn't exist. It doesn't work. Okay, let's go the other way. What is f of 2.5? Well, that's 4.5. So right away I know if f of 1.999 is 3.999, f of 2.5 is 4.5, then if f of 2, or the limit as we get really, really, really close to 2, has got to be somewhere in between these. So what is f of 2.1? Well, that's 4.1. What is f of 2.001? Well, that's 4.001. So now we know that from the left, here we were approaching from the left, the value was getting really, really close to 4. And as I approach from the right, it's getting really, really close to 4. So I'm going to go ahead and fill in this table, which you probably already did. See, this was 3.5. This was 3.9. This is 3.999. This was, I'm going to say D&E doesn't exist. This is 4.001. This is 4.1, and this one was 4.5. Now, although x cannot equal 2, as we can see there, we can move arbitrarily closer to. We can get a lot closer to 2 from the right and from the left than what we did. I can make this 1.999 and 999 and 999, and this 2.0000000000000000001. So I'm getting really, I'm squeezing in on 2. I'm getting really super close to 2. Now, notation-wise, what we say is we want to know what the limit is, so LIM, as x approaches 2. And this notation is telling me I'm coming from both the right, going this way, and the left, going this way, of f of x. So I want to get infinitely close to 2 on f of x. So what is the value of f of x? What's the y value when I get infinitely close to 2 on the x-axis? Now, we can go ahead and produce a graph of this using pre-calculus type techniques. In pre-calculus, we would have said, all right, f of x equals x squared minus 4 over x minus 2. And I'm going to see if I can't factor this, which I can. So this is going to be x minus 2 times x plus 2 over x minus 2. And the x minus 2's are going to cancel. So this equals x plus 2, specifically for x not equal to 2. You can see if x equals 2 here, I'm going to call this g of x. And I'm going to make another statement here. I'm going to say f of x is equal to g of x. It is. For all, if you haven't seen this upside down A thing, this means for all x not equal to 2. Because f of 2 equals, it doesn't exist. That's that 0 over 0 thing that does not exist. But g of 2 is equal to 4. So if I'm going to graph this, all I'm going to do, and I'm sure you remember this from pre-calculus, is I'm simply going to graph x plus 2. And then what I'm going to do is I'm going to add to it when x is equal to 2. Let's see, x equals 1. Here's 2. This is undefined, so I'm going to put a circle there. There's a hole in my graph. As x approaches 2 from the right, along the graph, I'm getting infinitely close to 4. As I approach from the left, as x approaches from the left, on the graph, again, I'm getting infinitely close to 4. So what this is actually telling me is that this limit, I can go back to this limit statement, say the limit as x approaches 2 of f of x is actually equal to 4. I'm getting infinitely close to 4. That's the limit. That does not mean that f of x equals 4. That does not mean that. In this case, f of x at 2, f of 2 is undefined. There's nothing there. There's a hole. Now, we can graph this very quickly in Maple. So I'm just going to say plot f of x. X equals, I don't know, how about -2 to 5? That should be good enough. And y equals -10 to 10. We can adjust that. So here's my line. When x equals 2, it looks at this thing actually equals 4. Well, see, what Maple does is there's no way, I guess you could put a circle there or something, but because this hole that we saw when we worked it out and I drew it for you is infinitely small, it's kind of hard for Maple to show you an infinitely small hole. So by looking at this, you cannot tell that there's a discontinuity there. So you got to be careful when you're using your calculator or Maple or anything to produce graphs, because these discontinuities of this type of discontinuity, this type of hole, you will never see.